Okay.
Some background here while Ken gets this up. This is a presentation. It's pretty high level. I'll try to get into some details about it that might interest some of the more technical people. I gave this presentation with a colleague, Michelle Tinner, last year at the Northeast, it's like Home Performance Conference. So this presentation was geared towards, I mean, I guess more like tradespeople and people on the ground doing the actual weatherization work. So it's kind of high level, but I'll get into some details, and I'm sure Ken and Wes have some stuff they'd like to add about it because they're pretty knowledgeable about it, probably much more knowledgeable than me.
I will probably, yeah, we will interject, but I think it's probably we want to keep this conversational and convivial. So if people have ideas and want to jump in, if you're okay with that.
Oh, absolutely.
Today, well, okay.
Yep. Oh, thank God.
All right. So, can y'all see this?
I can.
Yep.
All right.
Yep.
Brilliant.
All right, Ken. You want this to be like a half hour, right?
We try to keep it under 3 hours because folks have to get on with their days. So.
All right. I'm gonna rush through some of this stuff. Just because this is like an hour presentation, I'm gonna try to cut it in half. So we'll gloss over some things, and like Ken said, we'll be a little more conversational about others. All right, next slide, Ken.
Okay.
Keep going.
Okay. You're helping people build better. That's good.
Yep. All right, so we're going to talk a little bit about what's electrification, what does it mean, why it's important, and why we're seeing kind of a policy shift towards making it happen. And then finally, we're going to talk about how we actually accomplish this and how we make it happen. There's all the systems in a building. We're looking to move away from fossil fuels. So we're looking at heating, hot water, and then we're also looking at other ways of making those systems work better, whether it's through renewables or energy storage and electric vehicles, and features like demand management, which we're slowly seeing come into play. Next slide, Ken. All right. Yeah, let's just skip over this. I don't need to read this. And skip this. It's a fun picture. All right. Why do we want to electrify? Obviously, I mean, most of our business is built around, reducing CO2 emissions and other emissions that come along with fossil fuels. We have some serious issues with aging gas infrastructure, foreign oil, energy independence. We also want to help support renewable energy integration. And then, we primarily work in New York State. We're also in Massachusetts and Connecticut, but New York State has a pretty strong vision for reforming the state and how affordable housing uses energy, and we're seeing a lot of policy shift towards that, whether it be natural gas moratoriums as well as incentives towards electrification. There are some pretty serious incentives going on in both New York and Massachusetts, and so hopefully, some of these things will help people working on these projects actually get to fully electric buildings. Next slide. Let's keep going. And let's keep going. Get to the meat of it, Ken. And next slide, I'm not going to talk about this either. This is boring. Keep going. Let's get to the technical stuff. All right, here we go. Go back one, Ken. We'll actually talk about that one a little bit. You can see a pretty significant difference in CO2 emissions by state. New England is pretty far up there. Massachusetts, we're down right around 334 grams of CO2 per kilowatt hour by state. New York is 206. They're pushing to be carbon neutral by, I think, 2050. So that's a pretty progressive goal. I don't know what Massachusetts is in terms of their goal, but definitely something that we're working on now, and we have to impact a significant number of buildings in order to reach that goal. Keep going.
Well, and it looks like sunny Vermont has the lead here.
Yeah, the green state.
Yeah.
They're pretty good. All right.
I would just add, though, they are relying a lot on hydropower from Quebec, so it's not all super green.
That's a good point. It's a good point. Damon might have something to say about that.
Thank you, Peter.
All right, next slide, Ken. All right, so in the past, we've looked at electric, people know electric systems as, primarily electric baseboard. We're seeing, back in the 70s, there was a oil crises and gas shortages, and people moved to electric heating, and electric baseboard is, terrifically cheap. And that's what a lot of people think of when they know about, electric heating. And so now we're trying to transition to something a lot more efficient. So let's go to the next slide. And we'll go over some of these systems, from inefficient to some of the more efficient units. I've got some new technologies that are coming out. Next slide, Ken. Electric resistance. It's got a COP of about 1. Basically, 100% of the energy that goes into the electric resistance heaters get translated into heat. And while that may sound good, we can do a lot better than that. Electric resistance has its places. You might use it in small bathrooms or something like that, where it's not cost effective to use other systems. It's very cheap to install, besides for very small spaces, but it's expensive. It's not the most efficient, and it also puts a strain on the grid and can result in high demand charges. So next slide, Ken.
Can you explain, before we do that, can you explain what COP means?
That's a good point, Ken. COP is coefficient of performance. Basically, it's simply a ratio of how much energy you put into a system versus how much energy you get out of a system. So with heating, if you want to compare it to BTUs, you can put 1 BTU of energy in, and you get 1 BTU of energy out in terms of heating. In fossil fuels, they're not typically compared in COPs, but you can think of it as, you put 1 BTU's worth of, natural gas heat into the house, you actually lose a bunch of it out of the chimney. The exhaust gases and stuff like that are kind of considered lost heat. Heat pumps move in a different way, where they're not creating heat like electric resistance is or fossil fuels are. They're simply moving it. So electric resistance heat, look at that, Kevin. No, you can go to the next slide. We'll get into how heat pumps work a little bit. But basically, heat pumps use, a type of refrigerant, whatever that may be, and kind of a vapor compression cycle in order to move heat from either outside to inside or inside to outside, depending on whether you're heating and cooling. So it's a completely different way of putting heat into your household. With fossil fuels, you're burning something and using that heat that comes off of it, while heat pumps just kind of move it from one side to the other. Air source heat pumps, that's mostly what we're seeing right now. We'll also talk briefly about ground source heat pumps, but the COP, that's going to be dependent upon outdoor temperature. The lower the outdoor temperature is, the harder it is to pull heat out of it. But you'd be surprised, a lot of the newer heat pumps can actually pull heat out of, -10, -20 degree air. Obviously their capacity is reduced, the efficiency goes down, but even, climates like Maine and Canada, they use heat pumps successfully. Next slide, Ken. So what we have here are just a quick overview of air source heat pump components. Top left, you can see the outdoor condenser unit, and basically that's what's being exposed to the outside air, and that's how heat is pulled from the outdoors. And then pretty much the remaining pictures are all the different types of indoor units you can have. And it's not limited to this because they're coming out with kind of different creative solutions all the time. But you can see next to the condenser unit, there's a picture of kind of a wall mount unit, which a lot of people are familiar with. Next to that's a floor mount unit. And then bottom left is a ducted unit. So you can install that in the ceiling, in the wall, in the closet, and basically run ductwork to whatever room you need, which might be handy if you have a bunch of spaces with really low loads. Next to that is a ceiling cassette, which is good. It doesn't take up any space, pretty low profile. And then you start seeing some other creative solutions like this LG, forget what it's called, but it's basically, they built a picture frame on top of a wall-mounted unit, so you can throw some art in there and hide your distribution unit. So it's got all the technology behind it. It looks like a piece of art. It's kind of offset from the wall, like 5 or 6 inches. So let's go to the next slide, Glenn. So the first thing we're going to talk about is a mini split system. People have different terms for these different systems. Mini splits, most people tend to think of it's a 1-to-1 unit. So you have one outdoor compressor and one indoor unit. Multi-split systems, which we'll get into later, have one outdoor unit and many indoor units. And so we like to see mini split systems in buildings because usually they're typically the most efficient or one of the most efficient air source heat pumps. The outdoor unit is perfectly sized for the indoor unit, which kind of makes it run as efficiently as possible. They're coming down in terms of sizing, which is important as we're looking at passive house and really low load buildings, small apartments or small rooms. Oversizing really creates an issue with efficiency. So when you have a small apartment and the load during the coldest day of the year is only 4,000 BTUs, having something a 1-to-1 heat pump, a mini split system that can operate down near that capacity is going to be key for your efficiency. So you can see here, you have the outdoor condenser and then some sort of indoor unit, wall mounted, ceiling mounted, even possibly a ducted unit to kind of serve whatever space you're in. So up in the left-hand corner, you can see usually like a seasonal efficiency would be a COP of around 3. We've seen poor installs that you get COP, 1.5, even close to 1. Usually that's kind of an installation problem or a location problem, but usually you can kind of expect like an overall winter value of 3, a COP of 3 there. Next slide, Ken. Multi-split systems, this is where there's one outdoor unit and multiple indoor units. So basically you're running a number of refrigerant lines all to the outdoor unit. Can serve, typically, up to 5 zones. So if you're kind of pressed for outdoor space, you don't want a lot of condensers. You throw one outdoor unit in, run all these refrigerant lines, and they can serve, a bedroom, a kitchen, living area, even the second floor. We typically see them as being a little bit less efficient than a 1-to-1 mini split. as you know, the outdoor unit is usually sized for your whole building heating load. So it can be oversized if only one of your zones needs heating. So if you know, at nighttime, you know, you turn the temperature down in your living room and your kitchen area and you only need heat in your bedroom, now you have this big outdoor unit that's serving just one small indoor unit, and it can you know, heavily reduce the efficiencies there. It's not too bad as long as it's appropriately sized. That's the key thing. I'll get into that a little bit later, but HVAC contractors like to kind of size up. You know, that's always been one of the things they like to do. You know, they see it as a form of security, and that's not necessarily the case here. You always kind of want to correctly size it using a manual J or, you know, some other calculation, so you ensure that it's not operating, you know, in an inefficient manner. Next slide, Ken. And here's a VRF system, and VRF systems are unique because they can have really, really good efficiencies if they are installed properly and sized correctly. And basically what a VRF system is it can have, you know, one or two outdoor units, and then it serves an entire building, like a fairly large space. You know, you could do a whole office building, or you know, I've even seen them do, you know, large houses, 6,000 square foot houses or something like that. But basically, there is a large amount of refrigerant lines that move to different branch controllers, and they feed, you know, they can feed a huge number of indoor units. So like, for instance, like in an office building, you might have a wall mounted unit or a ceiling mounted unit, you know, in every single office space. And what's unique about it is it can handle both cooling and heating simultaneously. And while it's doing that, it's actually able to recuperate some of the energy. So if, for instance, you know, during, you know, May or June, when, you know, temperatures outside around here are, you know, pretty temperate, you might have the south side of the building getting, you know, heat from the sun while the north side is still cold in the mornings. When one side is cooling and the other side is heating, it can actually move the heat from one side to the other. So you kind of get this heat recovery effect, which can increase the efficiency of a VRF system by 10 to 15% over a, you know, typical other air source heat pumps. You have a little bit more upfront cost of these systems, but they can operate more efficiently than other air source heat pumps due to this heat recovery. There's also some added benefit where it uses a lot less roof space. You can see in that picture there, you know, a number of the VRF system outdoor units. And, you know, if you had a 1-to-1 heat pump for every single apartment in whatever building that's on, you might end up with 20, 30, 60 outdoor units versus, you know, these units, which, you know, you might have 4 units to serve an entire building. So if you're trying to, you know, site some PV or other stuff on the roof, this can be a better option. And you also have, you know, a whole lot less penetrations that the roofers need to flash, so you have, you know, a little bit less worry about, you know, roof leaks. And then there's also the benefit, this can be used for domestic hot water production. You know, the other air source heat pumps, you know, they're used primarily for heating and cooling, and you'd have to buy a whole separate system for domestic hot water, versus these, which can be tied in to a domestic hot water system, so you can kind of electrify your whole building in one go. One of the reasons we also don't see this as much on a lot of the affordable housing projects is it can be difficult to meter. You can't, you know, metering is a big thing in terms of charging tenants for their own heat or cooling. Sometimes owners, you know, don't want to take that cost upon themselves. And with this system, it's a central system, and you really can't charge tenants for heating and cooling for something like this.
Okay, Isaiah, is it all right if I jump in and ask a question?
Absolutely.
So on the last slide with a VRF system, what's a typical terminal unit? So is that at the end of the line? Is that an air handler?
You can do air handlers. A lot of times we see ducted units. So if this is feeding an apartment building, you might have a number of kind of small air handlers up in the ceiling that will feed a bedroom and in the living area. Office areas, ceiling units are pretty common, but I'm pretty sure you can use almost any of those previous terminal units I had on the earlier slide. Wall, ceiling, ducted.
So in a project that doesn't have operable windows, for example, you would need to pair this with a ventilation system to introduce the fresh air. Is that accurate?
Correct. Yep.
Okay. Thank you.
Yep, no problem, Kevin. This is what's called a Friedrich VRP unit, and this is kind of an interesting unit because we see it on a number of affordable housing projects. It's pretty cheap. It's a packaged unit. Basically, it's contained all in one. It's got options for bringing in fresh air. So it seems kind of like, a really good solution. It's got some issues, however, but basically, it's got a heat pump, a packaged heat pump, which is really, really nice. One of the problems we see with like VRF systems or any of the multi-splits or even mini splits is you have a lot of field installed refrigerant piping. And refrigerant piping, the more you have, the more likelihood there is of refrigerant leaks. And refrigerant leaks are bad for a number of reasons. Refrigerant is terrible for the environment. It's got an extremely high global warming potential. Typically, it's not a healthy gas. There's ASHRAE 15, which regulates how much refrigerant can be inside of a building or able to leak into apartments. And then also, if you have a slow leak, the equipment can operate really inefficiently as well. So this unit is packaged. Everything is installed from the factory. It's nice because it's got the ventilation option. It's got a MERV filter. It works down to 0 degrees. The only issue we see with this is it can be a huge air leakage location. It's a huge thermal bridge. It's just a big metal box that you stick into the wall. You can see it in this diagram. It's kind of placed on the outside wall. And it's 8 feet or 6 square feet of metal that just kind of leaks heat outside and then also leaks air outdoors. It's not NEEP listed. NEEP is kind of a rating body that Ken, you might help me out here. What does NEEP stand for? It's New England or Northeast.
Energy Partnership?
Northeast Energy Partnership?
Something like
Energy
that.
Efficiency Partnership, something like that.
Yeah. And basically they put out a list of approved cold weather equipment, and they don't have this on there specifically for the reasons that I mentioned. So it's a fairly cheap install. It's a fairly cheap unit. It's got its issues, but it also has its places, and usually has a pretty good COP when above 0 degrees. Obviously, a lot of the units that we look at need to operate down below 0, so this only works down to about 0 degrees Fahrenheit. Next slide, Ken.
All right, yes, sir. There's a bit of a lag here. It's updated on my screen, but not on yours. Well, plus I generally have a lag.
Here is the Minotair. This is a newer product, pretty small company. Ken, you might have more to add on this because I think you guys were actually doing some testing on it and have seen it in the field. But it is another kind of all-in-one magical box. It does air exchange. It's got the heat pump and can produce heating and cooling. It's interesting because basically it goes back and forth between bringing in fresh air and then recirculating air to kind of heat it up or cool it down. It's able to utilize waste heat from the fan motors to improve the efficiency. It's got a fairly low heating capacity, so it works for a lot of smaller passive house apartment projects. Might not work for like a whole house. Ken, what do you have to add on this?
Well, I would turn it over to Kevin Seaman, who's currently engineering a project to use this. But Kevin's muted. Oh, he's coming back.
Oh, thanks for the handoff there.
There you go.
Yeah, I didn't know much about this product until Ken and Wes added it to on the project we're looking at. But yeah, I mean, you kind of nailed it. I'd say it's got a lot of unique properties to it. With the self-balancing fans and all. Its claim to fame is that it kind of does cyclic ventilation as opposed to an ERV, which would constantly run the minimum amount of fresh air. It kind of calculates what it needs over a course of an hour, and you can use it for a bathroom exhaust system. So it can be your bath exhaust and your kitchen exhaust, not the hood, but the area in general. And then as that heat is exhausted, if it's summer or winter, it actually recaptures that energy through the refrigeration cycle. So it's kind of using it to preheat or pre-cool the air coming in when it's in that vent mode. And then it goes back to recirc. So there's quite a lot going on in a really small box there, MERV 14 filter and things of that nature. But it's definitely, it's got it, like you said, definitely has its applications. Has to be kind of a small apartment, and even in our application, the apartments have another form of heat. So this is really it's doing some, early heating and such, and tempering of the air for sure. But there is another layer of heat that's available. So that's good.
I think you guys pointed out last time that it's it needs a lot more space than it lets on because of all the duct work and everything that's required with it. So it looks like a small box, but once you add all the ductwork coming off of it, it needs kind of a full closet.
For sure.
Yeah, but it's an interesting niche, and we may see more of this. I think we don't see it now because it's a chicken and egg kind of thing. Nobody's doing it because nobody's done it. So we don't see many of these around, but it's an interesting solution perhaps for retrofit or new construction on smaller units.
Yeah, that was the feedback we got. We proposed it for one of our retrofit New York projects, and the owner was like, "What is this? How big is the company? How long have they been around? We don't trust it. If they go out of business, we have nobody to turn to."
All right. Well, wait a couple years. You may have a different picture.
All right, next slide, Ken. Now there's some more about it. All right, we don't need to go over this. This is kind of rehashing what I already talked about. Let's go to the next one. Best practices for air source heat pumps. Went too far, Ken. All right.
Got ahead of myself.
Systems operate better without setback. Basically, it's not necessarily recommended to use, a programmable thermostat with this. With oil and gas and fossil fuels, it's can be a good energy savings if you lower your temperature at night, down to 60 degrees, something like that, and then kick it back on to, your 68, 70 degrees, whatever you have it at in the morning. With air source heat pumps, you don't necessarily want to do that. That's, you don't, these heat pumps operate kind of best on partial load, and they operate best when the temperatures are warmer. And so if you're cranking these systems up at 6 or 7 in the morning, that's usually towards the coldest time of the day, and you're also, trying to make up some temperatures because you're trying to bump it up maybe 5 or 10 degrees or whatever. And so if you don't operate at a setback, it actually works much more efficiently than lowering the temperature at night. The systems also work best if you have a well-insulated, well-sealed house. They don't necessarily work great in old leaky homes, so it's kind of best to tackle the envelope and enclosure first, dealing with kind of air leaks, your enclosure and assembly. Deal with that first. Sizing, I've mentioned that a couple times. Sizing is huge. Make sure when these systems are designed, they are designed for the building, with realistic conditions. Don't, oversize it by 20%, just because, that's how, a lot of contractors have done it for 20, 30 years. Size it correctly and for the actual building using a manual J. Yeah. Let's keep going, Ken. Keep going. Ground source heat pump. Doing a couple projects with ground source heat pump right now. There, in New York at least, there are a lot of incentives for this. Ground source heat pumps can be done a number of ways, but the primary component of this is a well field where basically water is pumped through pipes to pull heat or reject heat to the ground around it. There's pretty much a big pump that circulates water throughout these, goes to a heat exchanger, or can go straight through the building. But basically, see these mostly with hydronic systems in the building, and they can be done through water source heat pumps that are located in apartments. You can use a kind of a central heat exchanger and heat pump to heat up the water that gets distributed throughout the building. You can supplement with gas-fired boilers. We see that a lot, where a lot of people are uncertain about the capacity of the system, so they have gas-fired boilers, which heat the building loop up to whatever temperatures they need it at. It's got very high efficiencies, but it also has a very high upfront cost. And if it's not set up correctly, you can have a number of issues. So they're fairly complicated systems, but when operated correctly, they can be very efficient. And sorry, Ken. Again, with the ground source heat pump, just like the VRF system, it does have the advantage of being readily transferable to domestic hot water as well. So, which is a big plus. We struggle a lot of times to get good electrified solutions for domestic hot water. So ground source heat pump, a water-to-water heat pump will allow you to produce domestic hot water pretty readily. And yeah, you can skip that one. All right. So that was heating and conditioning. And I apologize, I had some updated slides which did not get into the saved version that I sent over to Ken. So we'll just jump into water heating. There were supposed to be some more slides there. And we don't need to go through this. Next slide, Ken. Electric resistance. Everybody knows it. It's the cheap thing, cheapest upfront cost, pretty expensive to maintain or pretty expensive to operate. Doesn't require any venting, can be installed in a closet. They can last 6 to 7 years. So yeah, that's kind of historically what you see for electric systems. Here is something that gets brought up by a lot of teams. Electric resistance point of use. Basically, instead of having a tank with electric resistance coils inside of it, you have these little point of use heat exchangers that kind of heat up the water as they go. They are not great. They basically need one at every hot water outlet. It's very minimally more efficient than the electric resistance tank. And it requires a very high electric demand. Sometimes it requires, if you're going to retrofit this into a project, it might require upgrading the electrical service to deal with it. And then also over time, scaling occurs. Anytime you have water running over a hot surface, it might pull out some minerals and kind of coat that heat exchanger surface. So pretty much every time this is suggested, we shoot it down. So I wouldn't recommend this as a viable option for projects.
There may be some applications where there isn't a very high DHW load. Like
Sure.
I'm thinking of an office where you just have a hand washing load, or maybe a museum or something like that, where you're not feeding showers, you're not doing dishwashing or cooking. It might make sense, and it may be worth it to buy one of these every 3 years and let it go out.
Yeah, that's a very, very good point, Ken.
We have one in our office here.
Yeah, you guys aren't big on hand washing.
Yeah, it's a smaller storage tank, but it's a basically point of use.
Sure. Well, that's a good point. A lot of these, I'm in the mindset of apartments and residential spaces. So, like Ken said, sometimes the things that I'm discounting have their uses in other spaces that I don't deal with that often. So, good point, Ken. All right, integrated heat pump water heaters. These are kind of the first heat pump water heaters that are out, and they're becoming fairly common. You can get them at Home Depot now. You can see on the right side of the picture here, there's a storage tank with this little black heat pump unit on the top. And basically inside of that is, the whole heat pump system, and it blows air in, or it takes air in one side and blows it out the other. They're pretty high efficiency, but they do have their setbacks. One of the things is it's pulling heat from the surrounding space. So the efficiency of the system as a whole will be completely dependent on what you're using to heat that space with. If it's in a basement next to an oversized oil burner, that's fine. It's pulling all that waste heat from the boiler, and the basement might never get below 55 degrees even in the winter. But if it's in the closet of an apartment that heats with electric resistance heating, it's not going to be efficient because it's going to make up that heat using electric resistance. They also require a large amount of air around them, maybe 1,000 cubic feet, 700 cubic feet, something like that. So you can't just stick it in a closet like an electric resistance heater. There's design considerations. And as a result, like trying to integrate this into a multifamily project, it can be really difficult to find a good solution. Because you can't stick 10 of these in a mechanical room because it's going to pull all the heat out of the room. And once they get to a certain temperature, they're either going to operate really inefficiently as a heat pump, or they're going to turn to backup heating, which is electric resistance. And if that's happening pretty regularly, essentially, you bought yourself a really expensive electric resistance water heater. I think there are some cold climate heat pump water heaters that can operate down to a much lower temperature, but the majority of them shut off their heat pump operation, maybe 50, 55 degrees ambient temperature. So you have to be really aware of where you're putting it, how much space is around it, as well as how that space is being heated. It does have the benefit of cooling and dehumidifying the area in the summertime. So if you have a damp basement and it's down there, it'll pull a lot of water out of there and kind of act as a dehumidifier. If you want to stick these in apartments, you got to be aware that it will blow that cool air pretty much year round, so you might have some comfort complaints. It can be noisy and vibrate a lot, so you might get some complaints about the noise and in the cold air.
Yeah. So these are good points, Isaiah. I think so. As you touched on, to put this in a leaky basement for a fieldstone foundation in New England wouldn't make a lot of sense because it can't operate efficiently. It's going to suck the heat out of the air, and the space is going to get real cold. Someplace in Florida might make a lot of sense, because you're looking at cooling pretty much all the time, and you get free cooling as a byproduct of water heating. Where we found in multifamily, so notwithstanding all the challenges you mentioned, one thing we found when we get to modern multifamily buildings that are super insulated, they're cooling load dominated. So we like to get that cooling byproduct. And if these are distributed on a one-to-one basis, if you have the floor area, there's the advantage of you only run cold water piping through the building. So no hot water lines, no recirc. As an example, we looked at working on a 6-story multifamily building. The recirc line, hot water distribution recirc, accounts for over a mile of copper. So if we can pull that out of the project, that might actually be worth something. So that's just some other ideas around this kind of technology as it improves, as it gets better, where some applications may be.
Yep. Yeah, the best setup that we think there is for heat pump water heaters in these multifamilies is actually distributing them throughout the building, like you said, Ken, and kind of putting them in a closet off of the corridors. So you kind of if you have a double loaded corridor, you have them, maybe 2 or 3 per floor or whatever, depends on how big your building is. And they're actually using the corridor to pull the heat from. So that's if you need 1,000 cubic feet of air, the corridor serves that. And you don't need a recirc loop, like Ken said. You can pipe, one heat pump water heater to maybe the 6 apartments around it, above, below, and around it. And you don't need to add cooling to that corridor. So that can operate pretty efficiently. That's kind of the best case scenario that we've seen for operating it in a multifamily setting.
All right.
Yeah, here is another heat pump water heater that has taken off quite a bit, and we've been pretty successful in getting this on a lot of our projects lately. It's the Sandin split system heat pump water heater. And like your traditional split system, heat pumps that we saw for heating and cooling, this has an outdoor unit and kind of the indoor water storage tank. And so you can see that small outdoor unit. And what's nice about this is it's a CO2 refrigerant, which can operate very efficiently, even down to very low temperatures, down to negative 35 degrees. And basically, there's a water tank indoors, and it's piped. The water is actually piped to this outdoor unit. And it's nice because it doesn't pull heat from the conditioned space. It operates very efficiently, a little bit higher than even the other heat pump water heaters. It operates down to very cold temperatures. It does have a higher upfront cost, which has kind of been the deciding factor for a lot of teams. A lot of engineers are also worried about piping water to an outdoor unit. So if you have, really cold temperatures, they're worried about the water freezing. Doesn't seem to be an issue for a couple reasons. One is it's not piping cold water out there. It's piping, slightly, it might be 90-degree water. It's recirculating water from that storage tank to the outdoor unit. So it might be 90-degree water that is just heating up to, 125 or 140 degrees. So there's minimal chance of that freezing. You know, some people, you know, will run heat trace along it. You know, obviously the pipes are insulated as well. And the other concern is like what happens during a power outage. These have a drain back system, so you know the water will drain out of those pipes during a power outage and back into the tank. So there's no more risk than any other water heating system during those situations. So yeah, really good system. The VRF.
Can I ask a question about this?
What was that, Talon?
Just quick question. I mean, have you seen that CO2 heat pumps in any commercial applications?
I don't do a lot of commercial applications, Talon. I mean, we do. I mean, it's all residential. We've seen it in apartment buildings, and the thing is, it does need a lot of storage. You might need 500, 600 gallons of storage, even up to 1,000 gallons of storage, because of the low recovery rate. They don't, you know, produce as much hot water as other systems, and so you basically make up for that by adding tons of storage into the building. So you might need to add, you know, 5 times the amount of storage you typically would.
So, what's really attractive about these CO2 refrigerants are, I mean, all the refrigerants we use is also, you know, like they are greenhouse gases, and
Yep.
With the decarbonization efforts coming up, I think these are probably the future. But is there any applications of these heat pumps for like building heating?
I think there is, and we can actually, Mike Reagan has unmuted himself, and he could speak for the Mitsubishi perspective.
Thanks a lot, Ken and Isaiah. I didn't want to jump in too quickly there. Yes, so Mitsubishi is actually going to be releasing our version of the commercial domestic hot water heat pump. It's currently slated for March, but I'm more safely referring to that as the spring, because I wouldn't be surprised seeing March turn into April. But yeah, so we are going to be unveiling our first domestic hot water heat pump for commercial applications, which will be a 10-ton module unit that is more of a hot water storage maintenance heat pump, as in it's connected to either one or a number of different hot water storage tanks that's just continually heating that water to certain set point levels.
So is there any application that, you know, like you can actually attach these heat pumps into some sort of an, you know, like, I mean, a forced air system, so you use it for heating the buildings?
So that much, to be perfectly honest, we are still waiting for quite a bit of engineering data on that approach. We are currently looking at it simply as the domestic hot water solution. I wouldn't be surprised if we see integration with other third-party equipment, just as you had mentioned, but for the time being, I don't think that that's going to be first wave of unveiling.
Mike, do you have any units that use ammonia as well too, other than CO2?
I'm sorry, one more time?
Do you have any units, or are there any units that use ammonia? I think.
I haven't personally heard of ammonia being used as a refrigerant outside of commercial refrigeration applications like large warehouse storage facilities. This is the first I'm seeing of CO2 being applied. Normally, we've seen that in the past in commercial refrigeration just because of the super high pressure and steel piping that needs to be distributed throughout. So this is an early CO2 introduction into smaller residential and light commercial applications. And most of that steel piping is, it's all local to the condensed unit itself, or very, very minimal.
Yeah, thank you. This is really helpful.
It's certainly something that's on the horizon, and we expect to see more of it once Mitsubishi breaks the ice.
Yeah, I think these units are the future. I mean, especially with decarbonization going on. I mean, soon, you know, like most of these refrigerants are going to be banned.
Completely agreed.
All right, this is a good topic, Ken. We need to have our own. I think maybe next time talk about domestic hot water solutions.
Yeah, hey Isaiah, I have one question on that topic.
Sure.
Have you guys done any research on heat pumps in existing buildings? Because it seems like that would be the much bigger challenge, both design-wise and economically, but also potentially bigger impact.
Are you talking
Because
about?
there's more existing buildings than there are new buildings.
Yep. No, I agree. I think we struggle with that. It's just because, I don't know, there's a large upfront cost and nobody wants to pay that for existing buildings. The Sandon unit is actually surprisingly the one we've had most success with lately, just because it gets them where they want to be with efficiency. And a lot of the older buildings we have just have giant basements that sit there, and you can add tons of storage. But yeah, I mean, I don't know. We haven't. Electrification overall of domestic hot water has been a struggle. So we've primarily seen this stuff go into new construction. I haven't seen too much of it going into existing buildings. Everybody just kind of goes, how much does it cost? Oh, okay. Well, let's just keep the electric resistance and we'll go with that. And yeah, new buildings, yes. Existing buildings, not so much.
No, that's about what I thought you were going to say.
Yep.
So
and for that matter, Isaiah, what I've seen is that a lot of it has to do with the development of new incentives for electric domestic hot water solutions. Though either those exist in a very limited capacity or they're just not yet written.
Yep.
I imagine the same presentation in 2 years' time is going to be very, very fleshed out.
Exactly. No, it's ongoing, and I mean it's encouraging what we're seeing right now. I think we're going the right direction. We're not quite there yet with a lot of stuff, and incentives, like you said, do make a lot of the difference. And I apologize, Mike. I've got a picture of an LG hydro kit on here. I probably should have had some Mitsubishi system on here right now.
That's fine. That's why I felt free to just cut in and interrupt you whenever I wanted.
Yep, absolutely.
Fair enough. We try to keep it ecumenical here.
So, like I said, domestic hot water has proved challenging. The VRF system, offers a chance to tack on the domestic hot water solution as well. So here is a picture of an LG hydro kit. It's vastly inferior to whatever Mitsubishi offers, I'm sure. And basically this is kind of a water-to-water heat pump or refrigerant-to-water heat pump that, uses a refrigerant to basically heat hot water. And this one has 2 stages, so it's got your domestic hot water that can be, stored at 120, or it's got kind of the higher output 180-degree options, which takes quite a bit more energy. And again, like any of the other heat pumps, large amount of storage because of the low recovery rate. I don't know if you have anything to add on that, Mike, but I have limited experience with these VRF add-ons. I've never seen one in action, so I'm just kind of parroting what I've heard.
Pretty much that covers it. I just like to refer to this as another type of fan coil in the VRF lineup. The system sees it exactly like a cassette unit or a wall mounted. It's just another fan coil on there.
Sure. Thanks, Mike. All right, Ken. And then, as I mentioned before, ground source. You can tag on domestic hot water to that, basically a water-to-water heat pump. We've also seen, I haven't seen personally, I heard about it from the engineer that I worked with, where basically they left the building's heating and cooling system as is, but they use ground source heating just for domestic hot water. They didn't have a lot of space, but they were able to throw some wells in next to the building under the parking lot that basically helped them move their hot water system, domestic hot water system, to an electric system just using ground source heat pump. Obviously, pretty decent installation costs. But yeah, fairly efficient. One of the more efficient options we see out there. Solar thermal. This is cool technology. I think this system has been kind of surpassed by the efficiency gains that we've seen in PV. This is, you can, there's different setups, but essentially you have roof mounted or, kind of field mounted panels that absorb heat from the sun, and somehow that heat is transferred to your hot water. You might have storage tanks, you might have a glycol loop that basically move the heat around. A lot of these, can have maintenance issues that come with it, require a significant area for the panels and storage tanks. And usually they don't produce all the hot water that you need. So you need some sort of primary system, and then this will be an auxiliary system. The feedback that I get from people in the energy efficiency industry is your money is better served buying PV panels or solar panels that convert sunlight into electricity, and then using the electricity to heat your water rather than trying to move the heat around using the glycol loops and pumps and heat exchangers and all that. So overall, a cool system, but I think PV has kind of passed it by. And so your money might be better served going that direction. Other things that we consider when recommending a hot water system, metering, central or individual systems, the systems I just discussed, some work better for individually metered and some work better for centrally metered. The location of the indoor and outdoor units, you might need a lot more storage, or you might need more space for outdoor condensers unit. Impact on the tenants, for instance, if you have a heat pump water heater that is inside the unit, tenants might not like that. And then integration with HVAC systems, like if you're already looking at VRF or geothermal, you can leverage those systems for your domestic hot water as well. So that kind of makes your choice a no-brainer. All right, let's go through this pretty quick. This is not my area of expertise, and I'm not the one presenting on this usually, so kind of go over it real quick. Distributed energy, using renewable energy closer to the source or towards where it's being used is going to be key. One of the challenges of electrification is the fact that some incentives are based on the source ratio, which means you have to account for transmission losses in the distribution of the energy. So if you, right now, like in New York State, you produce let's say you produce, whatever, how many kilowatt hours at a power plant, you're going to lose probably 60% of that throughout the transmission lines. So you actually pay a huge penalty for using the distribution system. But when you actually produce it on site or closer to where it's being used, you're going to have a lot less transmission losses, and you're going to get a much better site to source ratio than if you're using it from, maybe a hydroelectric dam in Quebec. Next slide, Dan.
It's
Go ahead.
kind of the corollary to COP, right? If you have a heat pump that has a COP of 3, well, the grid has a COP of 1/3.
Yep.
So you're, thereabouts, rough math. So you're kind of back to where you started if you're just using a coal plant or a gas plant somewhere else.
Exactly. Yep. And that's where this push towards PV on rooftops and parking lots and in fields is really going to make a big difference. We're not just trying to make systems electric for the sake of being electric. We're trying to make the system as a whole more efficient, and that means using electric systems while simultaneously making the grid much cleaner, much more distributed, and the production much closer to where it's being used. Demand management. This is kind of ties into Internet of Things or smart homes, but tying it into the grid, where basically you're kind of shaving peak loads off of the grid by controlling systems. So, you might give your utility company permission to run your dishwasher or your washing machine and dryer, stuff like that, where basically things are will only operate when there's much lower loads. I think I saw an interesting talk by the founder of Noresco a couple of years ago, where he discussed kind of a microgrid system where they set up the utility company or the local utility was actually able to control freezers in the local stores, tie into batteries in electric vehicles, and basically lower loads during peak times, like during the middle of the day when AC units are all on, while also pulling electricity from different battery sources such as electric vehicles. So it's kind of shifting loads around, shifting demand around, so you don't have these big peaks and valleys that you see. So this is, I think there's some pilot programs out there that utility companies are managing right now to help reduce the peak loads, which will hopefully reduce, the amount that different power plants have to ramp up and ramp down, which, can lead to a lot of emissions and a lot of inefficiencies in the system. So yeah, in a summary, we're trying to, integrate these efficient heating, cooling, hot water systems simultaneously while greening up the grid or using, more renewables in a distributed way. It's kind of, you got to think of it as a system. It's not just electrification for the sake of electrification. It's electrification while producing clean energy and getting off of fossil fuels. So yeah, that's kind of that presentation summary. And we don't need to go through this. I think we can call this done, Ken.
Okay. I'm gonna let you say thank you.
Thank you.
All right. Excellent. Well, thank you, Isaiah. Thank you for bringing that through.
Yeah, I think, obviously this offers us a good opportunity to get into the weeds in future discussions. Like I said, this is kind of a presentation geared towards a lot of, tradesmen and people on the ground, and it gives a really high level overview. And so I think obviously we'll probably want to have some good talks about the in-depth stuff in the future, probably domestic hot water being one of them.
And I think, yeah, and I know Peter did a lot of research in this area about domestic hot water and how that seems to be the kind of the last hurdle on getting us to electrification. It's kind of a no-brainer to go with heat pump for heating, cooling.
Right, and I think we kind of agree on the design aspect, the distributed thing. And I think that you can convince people that if domestic hot water is their only natural gas load and it can prevent them from having to run the pipe to the building at all, like if you can make an economic case for it.
Right.
So you got to get to that point, and then you're almost in.
Excellent.